Okay, so today I'm going to show you all my proof of problem 6, V.I. Arnold's mathematical methods of classical mechanics. This is problem 6 of chapter 7, which is a chapter on differential forms. So the problem gives us D1 and D2, two compact convex polyhedra in the oriented k-dimensional space Rk, and f is a function from D1 to D2, which is an orientation-preserving diffeomorphism of the interior of D1 onto the interior of D2. Then the theorem states that for any differential k-form omega k on D2, the integral over D1 of the pullback of the form by the map f is equal to the integral over D2 of the form omega k. Okay? And it gives us a hint to use the change of variables theorem. So recall that for the pullback, the way that you evaluate the differential form is you actually look at vectors in the tangent bundle to the domain of the function, and you can evaluate, let's say, a set of k of those vectors with a k form. If you know a k form on the codomain, and then you just push those vectors forward under the differential of the map f, and evaluate the push forward of those vectors under the differential, i.e. the image of those vectors under the differential, which locally in coordinates is the Jacobian, and you evaluate that frame of k vectors by your form omega k, which is defined on the codomain. Okay, so that's the definition of the pullback of a differential form. And so the proof of this theorem is here. Okay, if Sol will let us prove the theorem. Hey, Sol. Proving a theorem, buddy. Okay, so let omega k belong to this, be a k form on D2, and D2 is a subset of Rk, okay? So this is actually a volume form, it's a top form. Okay, so our proof of this claim that the integral of the pullback of the differential form is equal to the integral of the differential form over D2. So first, partition D1 into cubes of side length epsilon and centers xi, okay? And then this integral, by definition, of this form, which is the pullback under f of omega k, is the limit as epsilon goes to 0 of the sum of this differential form evaluated at some at the frame of these epsilon cubes. So this is the vector frame of the epsilon side length cube. I'm sorry, my cat is playing with something. Come on, Betty. We're making a video. Go on. Stop it. Come on, bud. Go on. Good boy. Sorry about that. Okay, so we are taking the vector frame of this cube of side length epsilon, and that's just given by the canonical Cartesian frame, and we're evaluating that frame with this volume form, this k form here. And then we're summing over the Riemann partition. So this is actually the definition of the integral itself. Now, this is equal to, well, if we use the definition of the pullback here, we're going to go ahead and push forward each of these vectors, epsilon e I, each of these canonical basis vectors under the differential of the map f. And what we end up with here is the column vectors of the Jacobian matrix in coordinates, okay? So this is the differential push forward of E1, etc., through EK. The differential push forward of a unit basis vector, Cartesian unit basis vector, is just the column vector of the Jacobian in coordinates, okay? And this is all evaluated at f of xi, where xi is the center of the cubes that form the Riemann partition, okay? And so now we recognize that, well, the evaluation of this top form on this set of column vectors of the Jacobian, since this set of column vectors, we're assuming it spans the entire space Rk, because remember, f is a diffeomorphism, so the Jacobian will have full rank. and these vectors will span all of our k. And so we can, of course, the algebra of these forms, of these differential forms, agrees with the algebra of determinants. So in particular, we can manipulate these vectors using row and column transformations as we see fit, and the linearity, or the way that things will scale, is will follow the algebra of the determinant. And so we can essentially transform this using row operations. We can transform this set of basis vectors just into the canonical frame of our Cartesian cube of just side length epsilon, and in doing so, we're going to have to scale by a factor of the determinant of this matrix. Okay, and to put so basically we rearrange these vectors so that we get it in the form of a Riemann integral over the canonical epsilon cube partition with centers at f of xi. But in order to do that, we're going to have to manipulate this set of vectors and using row transformations. And in doing so, we're going to get a factor of the determinant of the differential, or the determinant of the Jacobian. We're going to get this factor on the outside. Now notice I've put this in absolute values, but since we are technically using the fact that it's orientation preserving, so since this map is orientation preserving, when I scale, when I do this these row transformations to get this in the form of the canonical cube, what's going to happen is the sign of the determinant of this Jacobian is going to be positive because it's orientation preserving. Okay, that's actually the definition of orientation preserving. So I didn't actually need an absolute value here. We know that it's positive due to the fact that f is orientation preserving. And then the final step is the change of variables theorem, which is a theorem that I actually covered in a previous video. I gave a full lecture on this theorem in full detail in RN. So if you haven't seen that, please check it out. But this is the last step. So to go from here to here, at this point, we're just dealing with a Riemann integral because this omega k is going to be a top form, and so it's basically due to the assumptions of d1 and d2, we're going to be able to just write that as a function times the canonical volume form, and we're just going to be integrating that function over Rk, and we're going to be able to use the change of variables formula to conclude the proof. Okay? So I hope you all enjoyed that video, and please check out Arnold's book on mathematical methods of classical mechanics. It's a really excellent book.